What if you could shoot groups like this, right from your kitchen table, with dice? That might seem crazy, but we created the most boring board game of all time that turns shooting groups into a hands-on dice game, simulating the same dispersion patterns you'd see at 100 yards, sample size noise, fliers, all through statistics. The dice handle the probabilities, so you can get a realistic target without firing a shot. I'm Chris Haig with Haig & Sons Precision Gunsmithing, and this is Shootin' Dice. The game comes with instructions, 2 boards, a few transparencies, a laser cut compass, and a handful of dice. So grab some coffee and let's get to it. Before we start on the main game, we're actually going to flip this board over and play the bonus mini game first, simulating muzzle velocity, since it's easy to recognize the terms and will familiarize us with the game's mechanics. Muzzle velocity follows a normal distribution, a bell curve. This curve represents the probability of an occurrence. It is centered on the average velocity, and the spread is defined by the standard deviation. The larger the standard deviation, the larger the extreme spread from high to low. With dice, we can simulate this very closely. Every roll of the dice is like firing a shot over the chronograph. First, the D4, the 4-sided dice, acts like a coin flip. Since this is centered around our average velocity, 50% of the shots are going to be above our average velocity and 50% are going to be below. If we roll a 3 or a 4, our shot is above the average velocity. If we roll a 1 or a 2, our shot is below average. Then we have these 3 dice. There's 2 D6s and a D8. These allow us to simulate a normal distribution very closely in half standard deviation increments. By taking the lowest number rolled from these 3 dice, those rolls relate to half standard deviation increments away from the average velocity. Let's try it out. We got a 2, which means our shot is below average, and our lowest number of these 3, is a 1. So we'll mark that there. We got a 2, so our shot is again below average by 2 half standard deviations. So we roll a 2. Below average again, with 1 again. Below average again, with 2. Below average again, and 3. So we can see that we are clustered actually pretty closely together, but we rolled below average 5 times in a row. So that means that that's going to affect the average velocity of this sample, and we can see that in a little bit. But first, let's calculate our extreme spread. So our true average velocity, let's say it's a 6.5 Creedmoor with a 26-inch barrel, will be right around 2750. And our standard deviation, let's say it's 10. That's a pretty good guess, and it also makes the math really easy for this example. We shot 5 shots, and our lowest SD rolled was negative 1.5. And our highest SD rolled was negative 0.5. So, if we multiply our lowest SD rolled by our standard deviation, we get negative 15. And if we add that to the true average velocity, our lowest velocity shot of those 5 was 27.35. And our highest was negative 0.5 times the standard deviation plus the true average velocity, which was 27.45. So our extreme spread is only 10, but our average velocity is going to be between the lowest velocity and the highest velocity shot for this sample. So if we were to base our ballistics off of this 5-shot group, we would have an inaccurate average velocity to base our ballistic calculators off of. And we can calculate at least an estimate here. So by taking the count of each of the standard deviations rolled, so at negative 5 we had 1, at negative 1 we had 2, and at negative 0.5 we had 2 again, for a total of 5. If we multiply these, we get negative 1.5 here, negative 2, and negative 1. If we add all these up, we get negative 4.5. If we divide this number, negative 4.5, divided by our sample size of 5, we get negative 0.9. So, if we multiply this by our standard deviation of 10, we get negative 9, and if we add that to our true average velocity of 2750, we get a sample average velocity of 2741. So if we were to base our ballistics off of this, our ballistic calculator would think that we're shooting almost an entire standard deviation lower than what the true velocity for that load is, just because the 5 shots that we took over the chronograph are telling us that our average is 2741 because we rolled below average 5 times in a row. So let's take this to a statistically valid sample size. So let's keep rolling. But we're going to use a different color. Below by 135. So now our sample size is 35. Our lowest SD rolled was still negative 1.5, and our highest SD rolled was the full 3. So our lowest velocity was still 2735, but our highest velocity now was 2780. So our extreme spread now is 45. And if we do this calculation again,
2 here, 7 at -1, we have 9 at -0.5, we have 5 at +0.5, we have 7 at +1, 1 at +1.5, 2 at +2.0, we have 1 at +2.5, and 1 at +3. So, we multiply these across, we get -3, -7, -4.5, +2.5, +7, +1.5, +4, +2.5, and +3. Okay, so below average, we have -14.5, and above average, we have 10 plus 21.5.
so there's a difference there of +7 divided by 35 equals 0.2. So, if we multiply 0.2 times our standard deviation, we get +2. So, and if we add that to our true average velocity, our new sample average velocity is 2752. That's really close, and since our standard deviation is 10, that means 66% of our shots are going to be plus or minus 10 from this number. So that too does get absorbed or eclipsed by the standard deviation. And we can see that being 2 feet per second off when our 35 shot extreme spread is 45 is pretty close. But it's not perfect, but it never will be. But we're trying to minimize the amount of error. So let's take this strategy and the mechanics of this game and the dice, and let's take this and apply it to the main game. But first, we have to go through a bit of statistics differences between muzzle velocity and shooting groups. In muzzle velocity variation, all the data is distributed on a single axis, and it's distributed in a normal bell curve distribution. That bell curve is centered and anchored by the average velocity, and the spread is determined by the standard deviation. In group dispersion, the data is in two axes, the y and the x. This data can be thought to be distributed in two fundamentally different ways: by separating the x and the y into its Cartesian coordinates, and the x coordinates are distributed normally, and so are the y. But we can think about these coordinates in a polar coordinate. That is defined by an angle and a distance. Believe it or not, the angle is equally distributed from 0 to 360 degrees for groups. So, in other words, the direction that the impact is from the group center is completely random. And that can be simulated by using something like a 20-sided dice. The distance, instead of being normally distributed, since it is bound by 0, is distributed on something called a Rayleigh distribution. The Rayleigh distribution has an average, and that is the mean radius. We know mean radius from our group analysis apps. 50% of our shots are impact outside of the mean radius, and 50% of our shots are going to impact between 0 and the mean radius. You can see that the outside half of the Rayleigh distribution is very close to the outside half of a normal distribution, a bell curve. But between 0 and the mean radius, it steeply dies down to 0. And another interesting thing is that it can still be described using standard deviations, but because of a neat set of equations that define the Rayleigh distribution, the mean radius and standard deviation are equated to each other. The standard deviation of a Rayleigh distribution is equal to 0.523 times the mean radius, or the standard deviation is about 1/2 the mean radius, or the mean radius divided by 2. And so we can split up this distance between 0 and the mean radius by about 2 and denote this distance as approximately 2 SD. And then 99% of the data is going to be within 3 standard deviations of the mean radius. So let's take a look at how that affects our board. So in this board, we have our group center and we have our mean radius. And that mean radius is 2 standard deviations away from the group center. And then the rest of these rings are between 0 and 3 standard deviations away from the mean radius. On this axis, we have our half standard deviation increments, just like on the muzzle velocity minigame. But on this axis, we have our dice rolls. So outside of the mean radius, we have 1, 2, 3, 4, 5, 6, denoting the rolls from our distribution dice. But inside the mean radius, we stack the 2 and 5 and the 3 and 6 to more closely approximate the probability of distribution inside the mean radius on this 0 to mean radius section of the target. And to denote whether or not the shot is inside or outside, we use the same D4 dice to get a 50% probability of going outside of the mean radius and a 50% probability of hitting inside the mean radius. Just like in our velocity variation minigame, where the D4 denoted a 50% chance of being above your average velocity or below your average velocity. So, now that we know the statistical differences between muzzle velocity variation and group dispersion, and we know how the mechanics of the dice work in conjunction with our board game, let's play. So we got a 13, a 3, and the lowest number of these is a 1. And line 13, we're outside the mean radius, and we rolled a 1. So that's our first impact. So if we do this a couple more times, 3, 19, and 1. Sorry. So we're inside the mean radius at line number 19, and our lowest number is 1. 13, again, outside the mean radius, and our lowest number is 5. So that's way out here. Got 11 outside the mean radius, and our lowest number is 2. Inside the mean radius at 18, and our lowest number is 1. So that's right here. So now that we've marked our 5 initial shots, we can scale this, and we can scale it to the mean radius and the caliber that we're wanting to shoot using this impact sizing chart in the instructions. So what this chart shows is a series of letters that are correspond to a radius from this crosshair to any of these letters on this chart. And that will actually scale this target to the mean radius and caliber of what we're trying to represent here. So the cards that were shown at the very beginning of the video were shot with a 6mm bullet with a mean radius of 0.20. So if we're going to simulate groups from that rifle in this game, we will be using the radius designator V. So if we go to this impact sizing scale and we take a compass and place the point of the compass on the crosshair and the nib of the compass, or the nib of the marker, on the letter designator V, then now we have this compass set up to make impacts that are scaled to a 0.2 inch mean radius and a 6mm bullet. So let's draw our impacts.
With this compass on the 5 impacts that we rolled. There's 1. There's 2. There's 3. There's 4.
And then our last impact is here. And this is with a 243 with a mean radius of 0.2, and our number of shots was 5. And while we're at it, let's fill out this histogram. So we had 2 impacts that were right in the mean radius. Then we had one that was in the first ring, one that was in the second ring, and then one that was at 2.5. So we can see again in this histogram that they're mostly clustering around the average, but we have one outlier that is at 2.5 standard deviations. These impacts, believe it or not, could have happened anywhere, any direction in this target. These happen to all happen between 10 and 20, so we got a group that is somewhat left of center. But it would have been equally as likely for this impact here to happen anywhere along this ring. And if it were to happen over here or over here, then I think we would, if we were to see that at the range on paper, we would want to call that a flyer, but that's not how the statistics behind shooting groups actually works. And so we could have seen this impact at the 2.5 anywhere along here. Compare that with one of the groups that we saw at the beginning of the video. If we turn it this way, it almost looks the same. If we think of the bullet holes scaling each other. But if we were to use this at a competition to get a 0 for our rifle, we might get the elevation correct, but we would be somewhat off. And for the whole competition, we would be shooting left of where our rifle is actually, the center of our dispersion is actually going. So that's the danger of zeroing off of 5-shot groups, and that can clearly be seen here. Another thing we can do with this 5-shot group is measure the extreme spread. So if we measure our group on the target, we get a center-to-center distance of 3 3/8 inches. And if we divide that by this extreme spread scale factor on our chart with a mean radius of 0.20, it says 6.67. So if we divide our 3.375 by 6.67, we get an extreme spread of 0.506 inches. If we use the estimated 95% diameter for a mean radius of 0.20, we get an estimated 95% diameter of 0.80. So that's the diameter of this dashed circle. So 95% of our shots should land within that dashed circle. And here we got a little unlucky. And since we rolled a 5, we have an impact that is a radius from the group center that we wouldn't expect in 95% of shots. But because our other 4 shots grouped somewhat close, we got an extreme spread for this group of only 1/2 inch. Again, this group of 5 shots is not representative of what we can expect 95% of the time for a rifle that shoots with a mean radius of 0.2 inches. But let's keep rolling until we have a statistically significant sample size. (16) outside the mean radius by 1 standard deviation. And again, we're going to use a different color. So 16 is here, outside the mean radius. So our 6th impact is there. We don't have to trace all of these blue ones. 243, still same true mean radius for this load of 0.20, but the number of shots is 35 now. And we can fill in the histogram. We can see now that with 35 shots in our sample, our histogram is filling out the distribution curve much more like we would expect, where we're getting a lot in the middle. We got lucky with our D4 rolls, and we got more inside the mean radius than outside the mean radius. If we look at the extreme spread, going from this impact to this impact, now that distance is 4.375. So 4.375 divided by 6.67 equals. We get an extreme spread of 0.656 inches. So that's still not what we can expect from 95% of our shots. It is better. But this group will now produce a sample mean radius that's a lot closer to our true mean radius that we selected here. So what we can do is we can take a photo and for our measurement point, we can use the mean radius, the red ring on our target. And instead of putting 1 inch, we'll put 2 times the mean radius, which is 0.4, that we selected for our group. And now, if we select our bullet diameter as 6 millimeter and our distance to target as 100 yards, we can set the point of aim at the middle of the target and all our impacts, and you can see that the circles that we drew for the first 5 impacts using our scale on the compass perfectly align with the scaled impact in the app. So we'll add these first 5. And then we can add the other 30. So with a little bit of Hollywood magic, we can see that all 35 shots are plotted now, and that our group size of 0.66 inches perfectly aligns with our extreme spread that we measured on the target and used our extreme spread scale factor to scale to the mean radius and caliber of the load that we were wanting to test. And what we can also see is that the elevation and windage offsets are essentially 0, and the mean radius is 0.18 inches for this 35 shot group. And yes, that is slightly low, but we observed a higher than usual amount of shots that were inside the mean radius, and 0.18 inches is well within the confidence interval for 35 shots. If you don't have a physical board in front of you, no problem. You can download one of these boards and you can input it directly into the app by either rolling physical dice or digital dice like on Google. You can play directly in the app. So we got 14, 3, and 3. So that means we are aligned with 14 here. We are outside the mean radius, and our roll was in the 3 ring. And then you can build your target directly in the app. So why should you care about a board game that simulates group dispersion with dice? First, by starting off with the muzzle velocity minigame, we connected concepts most shooters already know: averages, standard deviations, and distributions. The dice break those ideas into hands-on steps. The D4 gives you a 50-50 chance of being above or below the average velocity, while the distribution dice simulate a bell curve surprisingly well, and we showed that 5 shots were not able to give us a reliable average muzzle velocity to base our ballistics off of. Second, when we moved to group dispersion, we applied the same mechanics but added an additional step. The D20 gives each shot a random clock direction. The D4 gives a 50-50 chance of the impact falling inside or outside the mean radius. And the distribution dice, paired with the board, simulate the Rayleigh distribution of radial error quite accurately. Together, it gives you a realistic way to watch your groups form shot by shot. And third, the game helps recalibrate expectations about what a load can really do. In the game, the mean radius is a known input. It sets the scale of dispersion, just like in real life. Keeping that mean radius constant is like testing the same load over and over. In small sample sizes, the groups bounce all over the place. But as the sample size grows, they stabilize and reveal the true capability of the load. The only way to see that in real life is to shoot a statistically valid sample size. This game teaches that in a hands-on and approachable way. If you want to try this game yourself, all you need are some dice and the downloadable boards linked below. I had a lot of fun making this board game, and I hope you have a lot of fun playing it. Thanks for watching, and remember, shooting groups is just like rolling the dice.